So now we've discussed the induced potential. Faraday, though, he talks about current, and we know that potential and current are related through Ohm's law. So let's see how that comes in here in Faraday's experiment. So let's start by taking our conducting bar and let's place the conducting bar on conducting rails. So we're placing them on conducting rails. These are the rails, and this is the bar. So now what we have is a circuit. So we've made a very simple circuit. So now let's ask what happens. We pull the bar to the right with some applied force. So there's our pulling force. Let's say that we're pulling it so that it has a constant velocity v. Here in our picture, our magnetic field is into the page. Now let's start to discuss what happens. We know, because we found on the previous slide, that the induced potential difference between the top and the bottom of the bar, because the charges feel force and they start to move and they start to separate, the induced potential difference is E, or epsilon, equals B times L times V. And this induced potential came from the charges moving up because they felt the force. Moving charges means there's current. So charges move, therefore there's current. And that's just the definition of current. Which way does the current flow? Well, any positive charge in this bar feels a force. So it's moving this way, the field is into the page, it feels a force this way. So the charges, positive charges, move up this way. That means that the current comes around our circuit this way. So the charge in the bar moves up, and for the circuit as a whole, it moves counterclockwise. So let's see what we can figure out about that current. From Ohm's law, we know that V is equal to I times R. Now let's put in the notation that we've already started to use. It means our current is equal to the induced potential divided by the resistance. Okay, let's make sure we know what we're doing here. Epsilon is the induced potential. It only happens because we move the rod. R is the resistance of the loop. So what this tells us is that I is the induced current. That means we only get this current happen, we only make it happen when the bar is pulled. If we leave it alone, there's no current. Now we'll add in that our induced potential is B times L times V. So that's the size of the current that's induced in the loop. When you looked at that video about magnetic braking, we know that when we move the conductor in a magnetic field, it slows down. So there must be a force on it. So let's talk about the magnetic force next. The magnetic force, and let's be really clear with our notation here, the magnetic force, FB, is equal to I times L cross B. I is the induced current. And B is the field that the conductor sits in. So it's the existing field. What direction does this force point? Well, let's think about our bar here. The current points up, the magnetic field is into the page, the magnetic force, the induced magnetic force, is to the left. So this explains about the magnetic braking, why that induced force is in the opposite direction. So this magnetic force here is a magnetic force induced on a conductor moving in a magnetic field. Something that's really important here is that this magnetic force always opposes the motion. So these induced magnetic forces will always slow it down. What next? Oh, we could have a special case. If it's constant velocity, then the magnetic force and the pulling force would be constant. We'll do some examples and we'll look at some problems where we see that those two forces would be equal and opposite, and we can find out some things of the problem. Let's ask one more question. If there's a current in this bar, what happens because of that? So if there's a current in the bar, let's remember what we know about current carrying wires. They make magnetic fields. So the current in the bar induces a magnetic field. What's the direction of that magnetic field, or what's the size of that field? Well, we know that B is mu naught times I over 2 pi r. So I is going to be the induced current, so we know what I is. R is your distance from your bar to the place where you're trying to find the field. And what would be the direction of that induced field? Well, you put your thumb with your current, and you know the magnetic field makes big circles around that wire. We ask what's the direction of the field right here. It comes up out of the page, so it's making circles this way, and at this point right here it comes out of the page. And we can draw those in if we wish. So there's our induced magnetic field. What else? Something interesting to notice here. The existing field was into the page. The induced field is out of the page. As you read ahead, you might learn a little bit more about that, but we will certainly come back to it. So it opposed the original field. Okay, let's take this one step further. We've discussed potential, we've discussed current, we've discussed forces. Let's also talk about the power in the circuit. So we'll keep going with our problem. And I'll just very quickly re-sketch what's happened here. So you probably already have this in your notes. Here's our conducting rails. There are the rails. Here's the bar. It's sitting in a magnetic field that points into the page. And it's being pulled to the right with some pulling force that gives us a velocity v. When the conducting slider, that's our bar, with resistance R, is pulled on rails with constant speed v, how much power is dissipated? So what's the power that happens here? Let's think about all the things we know so far. The current was the potential divided by the resistance, where the potential was BLV. The induced, so this is our induced current in the circuit. Our induced magnetic force is IL cross B. Everything's perpendicular, so ILB sine theta, where theta is 90, just gives us ILB. And that's an induced force. It only happens because we're in motion. Let's fill in what we just wrote down for our current, BLV over R, and then times LB, gives us B squared, B times B is B squared, L times L is L squared, times V over R is our induced magnetic force. What's the direction of this induced magnetic force? The current is up, B is into the page, the force is to the left. which we did on the previous slide, but it never hurts to do it again. So there's our induced magnetic force. So we can put in our direction minus I or to the left. So what's the power associated with that force? You may remember that power is change in energy over change in time, or work over time. Work is force dotted with displacement. I'll use delta x here for displacement because it's only moving horizontally. And then you might notice delta x over t, that's velocity, the constant velocity. So for this problem, the induced force is left, the velocity is to the right. So F dot V is minus F times V. Let's put in what our force is. So the power associated with this motion is minus B squared L squared V squared over R, where the negative sign shows that the power is negative, or that energy is being dissipated. Okay, now the next thing we'll do, and we'll go on to a new video for the next one, is we'll do an example with some numbers.